I am able to meet you because you decided that light should meet matter, and the whole program is on light meets matter. So we should always be aware of our limits in anything, whether it is a webinar or whether it is a research topic or whatever, or a scientific principle, even Newton's law, there are limits to it. So let us see what is the limit. Generally, people say sky is the limit. And that is a nice inspirational quote for students, whoever is starting research, anybody who is doing something, starting on some new venture. But actually, the limit is the blue sky. The blue sky is the limit for us who are interested in C.V. Raman and his work and inspiration he has provided. So generally, people are interested in the Raman effect. But there are two effects. Both I am going to talk about today. One is the Raman effect, which is a technical point. And the other one is the Raman's effect. Raman's effect in Indian science. Of course, in international science, but we are particularly interested in Raman's effect in Indian science. He is the one who systematically opened up a research laboratory and showed us how a laboratory should be set up, how an institute can develop in research. So he set standards for laboratory research, particularly in physics. So that is Raman's effect. We will touch upon both Raman effect and Raman's effect. I would not like to concentrate much on the Raman's history, family. That's not interesting. That's not important. What is important is what is the spirit that he has provided us, and what is the technical matter. A few students can please switch on your video so that I can see whether the audience is understanding or not. Please. Some of you can switch on the video, and audience can be muted unless you want to ask a question. Shall we proceed? Yeah. So let us look at the limits. The blue sky. And what do I mean by the blue sky is the limit? This is a story of light. Light, everybody knows about light, what light has given us. Light carries energy and information. I am able to see all of you. I mean, actually, I am not able to see all of you, but people are able to see each other because there is light. Not only because there is light, because light carries information. Scattered light. We are able to see each other because there is scattered light. And scattered light contains information. And that will be the theme of the talk. What kind of information does scattered light carry, and how does it? So the first research paper in optics had only one line in it, is let there be light. There are not too many papers by that author, but the impact factor is extremely high for whatever is available. A few conference presentation on a mountain and a book. There is tremendous impact, more impact than anything else ever written. Okay, so first, that is what happened. But then we have to remember that light can carry not only energy, but also information. And what happens when light carries information? We get information about various things around us, not only peripherally, but also inside, deep inside matter. That is what we are going to look at. And how does it happen? How do that we get information, and what kind of information we can get? That's what we will see. People talk about harvesting light. We are alive because of light. We are alive and happy here because of light, the presence of light. Unless we have light pollution, we continue to be happy with light, unless light comes at the wrong time and stay. So this brings up the paradigm of exploitation or exploring what all aspects of light-matter interaction. We have natural materials, we have novel materials, artificial materials, all aimed at this harvesting light. So in today's context, in the context of C.V. Raman's work, We are talking about how we can get information from the phenomenon of light-matter interaction. What is the physical mechanism which helps us to gather information, deep understanding of what is going on around here? In the molecules, in the deep heart of the matter, molecules മോഹിനിയാട്ടം നടത്തിക്കൊണ്ടിരിക്കുകയാണ്. ഈ മോളിക്യൂൾസിന്റെ മോഹിനിയാട്ടം, ഇതിൽ തന്മാത്രകളുടെ താളലയം, ഇതൊക്കെയാണ് രാമൻ സംസാരിക്കുന്നത് നമ്മളോട്. അതിനെക്കുറിച്ചാണ് നമ്മളിപ്പോ മനസ്സിലാക്കാൻ പോകുന്നത്. Let's look at the blue sky. Again, we will continue to talk about blue sky. But when we talk about the blue sky, we see many other things in the blue sky. For example, you see a very colorful object here in this picture. And that has a lot of physics in it. That tells us a lot about light-matter interaction. The wonderful, beautiful result that you see on screen is a result of light-matter interaction. This is what happens when light meets matter. That's why I like your title of your webinar series, Light Meets Matter. Color is what you see there. Is color physical, chemical, or biological, or psychological, or commercial? Color, we have a particular dress that's because of chemical color. But then, color has a lot of physics in it. The color which you see there is actually of physical origin. It is not because of the chemical properties of H2O that you see all the colors. On the other hand, a particular dye will give you fabric dress of a particular color. That we can call as chemical color. And biological color. Biological color also has physical origin to it. So that color is a little more fascinating than what you think at the first sight. And it's a deeper visualization of it. That is what is required, an understanding of that. And C.V. Raman was a co-traveler of light. Light, color, beauty, sound, everything. Solid state physics, all that. What he's holding in his hand is a diamond. He was interested in that, the colors of the diamond. He was interested in acoustic also, though it is outside the syllabus for our talk. I would like to mention a very important thing. The Indian musical instruments, Mridangam and other instruments, they were not known outside the world till Raman's work. But Raman published a paper in Nature describing how these Indian musical instruments work, the acoustics, the physics of working of Indian musical instruments. And that paper appeared in Nature, the West Journal. And then people all over the world came to know about it. And that made these things very popular. So Raman's contribution to Indian music is something not everybody knows, but it really happened. And people got curious with, this Mridangam which came in Nature paper, how it vibrates, Bessel functions and all that. Some of you may be knowing about this. The patterns created when a Mridangam vibrates that can be described by complicated mathematical objects, special functions and all that. So that's aside. Now coming back to light, he spent a lot of research on various aspects of color, apart from contributing to solid state physics and fundamental physics at a great depth. I would like to invite you to a paradise. We are all bored with the lockdown kind of thing and a lot of difficulties in life, so it would be nice to go and visit a paradise at this point. The paradise I would like to present before you is optics. Optics has phenomenon of polarization, absorption, reflection, amplification, diffraction. And if you look at it carefully, I have colored the first letters differently. And that is the paradise, the research field of optics. And all of them, each one of the phenomena listed there tells us a lot about many things. the universe at large, things around us, things inside us also, using fiber optic probe, for example, in medical situation. So that is a perspective of light matter interaction and the various phenomena related to light can give us as a part of light matter interaction. We are always asking this question, why is the sky blue? But is the sky blue all the time? Look at the background of this picture. It shows a non-blue sky. And when you think about it, a lot of questions arise in our mind. These questions are mentioned in a lecture by C.V. Raman for school students. This is taken from there. All these are taken from the quotes, and all these questions are taken directly from the book, the lecture given by C.V. Raman on why the sky is blue. You can get that book. I suggest that all of you, those who have not seen it, please download it from the web. It's available it's not available on YouTube and all that. At that time, videography was not that perfected. So you don't have videos of C.V. Raman giving this lecture, but it is a radio talk actually originally. And you have a PDF version available on the web. If you have a difficulty in getting it, you can ask me. I will send it to you. So Raman starts this by telling the sky is blue. The lecture starts like this. The sky is blue because the sky is there and I am here. That is the first statement. And it's full of such statements. Very interesting, meaningful, deeply philosophical statements. And of course, at a very simple way, so that you get a lot of understanding after that. For example, you think of, you talk about clouds when you think of scattering. Clouds are particles, dust particles accumulated, and they scatter. That is the color of the sky. So Raman says, well, it raises a lot of questions. What is a cloud? Many people, we all have confusion about what exactly is a cloud. Why some of them are black, some of them are dark, various shades, and some of them are white. Where are they? How high? At what height is the cloud or the clouds? And why are they at that height? And how do they float around? Why don't they fall down? There is water vapor there. Everybody knows that in many of the clouds, dark clouds. Why is ice colorless whereas snow is white? Both are H2O. If you have one molecule of H2O, do you call it ice or steam or water? There is a different question. The question here is ice is colorless, perfect ice, but snow is white. And if, okay, you remove all the clouds, all the scatterers. Suppose the wind comes and removes all the clouds from your visual, what you can see, the area you can see. Then the sky becomes even bluer. So what exactly is the secret of the blue sky? And then Raman asks this question in that book. Why is the sky not blue in the night, for example, at other times? Why is it not blue? So Raman gives equal importance to both this. Why is the sky blue? Why is the sky not blue sometimes? Both will give you a balanced version of that. So this is what Raman gives you. This is highly inspiring. Raman's book, this talk is highly inspiring. And if you haven't read that, you have really missed. And you can easily make up by spending half an hour to read it, to find it out from the net and read. It's called Why the Sky is Blue, a radio talk by Raman. So that's what we are all fascinated by. The sky is blue, the ocean is blue. Raman was traveling in a ship and he looked at the sky and the ocean. Everything is blue then. So previously what people thought, even scientists thought, okay, I can't understand. I answered two questions, why the sky is blue and why the ocean is blue. But I can understand the second question. The ocean is blue because the sky is reflected by the ocean. Later it turned out to be not correct. That's not the correct answer for that. Okay, we want to understand this. We want to get some meaning. By the end of this hour, we want to get some idea about all these processes. Why? What makes it? The deep levels of scattering. So we have to go step by step. looking at the spectroscopic aspects of light and then matter, both light and matter. We will go into light, we will go into matter, and then try to see what. People say, there is a poet who said, man will never be able to understand why blood is red and grass is green. You ask the chemists or biochemists, they will say, we know why blood is red. It's a molecule is hemoglobin. And why is the grass green? There are a class of molecules called porphyrin, which have a caged structure, and you put a different metal at the center of the porphyrin molecule, and you see different colors. That's one level of explanation. So this is what Raman starts. The sky is blue. That is a very interesting problem. The sky is there and I am there. Raman says the best way to answer a question is to ask another. So that will be made applicable for this lecture. If you have questions to ask, we will answer it in Raman's way, because it is a special day to remember and get inspired by C.V. Raman. Just think of it, meditate on it. The best way to answer a question is to ask another question. You see a little, and even this little is enough to elevate our mind. And to make us realize what a wonderful thing this world around us is. This is what happens when researchers go on vacation. You see a senior researcher going with family for a nice vacation. So she is asking, oh, you get away from all the research, everything, spending quality time with your family. What a beautiful moment. Just look at what is happening. But what do the scientists think about it? The scientist is not thinking about the serenity of the situation or the beauty or anything like that. He's thinking about molecules, scattering, Raman effect, and all kind of things. So there's no vacation for a scientist. If a scientist goes for a classical music concert, what will be? He'll be thinking of various mathematical functions which describe the various musical forms which come in, and he will do a Fourier analysis of music and see which are the highest frequency, which are the frequencies, to what extent the frequencies are present, and all that. I still don't see faces. I would like to see, then only I will know whether people are able to understand, or I should explain more. See, at the end of whatever, there must be some input, right? Am I audible properly? Am I audible properly? Abhishek?
Yes, sir. Yes, sir.
Yeah, if I can see some people, I can find out, get some response. Okay. So Apple's secrets are finally revealed. You know Apple's secrets? Why is the apple red? That's the question. So from sky, we suddenly go to something which fell from the sky. And apple is anyway of very great importance to physics. Right? So let's see why the apple is red. That's the question. The apple is red as red color is scattered all over the, and all the other colors are absorbed. That's the answer to it. So that's one level of understanding light-matter interaction. So when light meets the apple, this is what happens. We know when apple meets Newton, what happens. So apple is very important anyway. Scattering. So there is light, the source of light, and matter, and they interact. That is the reason for apple's color. Actually, apple is very interesting. Not only to eat, not only to drive doctors away, but it's anyway interesting. Youngsters, the teenagers of today all become of marriageable age, and you will have children. So this boy is asking the father, what are clouds made of? He says, I used to know. I think they're mostly water. Then how does it float? How does it float in air, water? The boy asks. Father says, well, it sort of evaporates. Maybe there are some other gases. I'm not sure. So why are they white and the rest of the sky is blue? He's asking a Raman question. Heck, beats me. I guess we ought to look this up. Then the boy says, I think there is no qualifying exam to become a dad. So you have some qualifying exam. You need some basic information before you become a dad or a mom. So that's why you should listen to this lecture and get some nice ideas. One reason, yet another reason why you should. Even in personal life, okay, I'm not going to become a big scientist. My plan is not to become a scientist. I'll become a some big businessman or something like that. Fine, but then when you're a human being, you're a person, and there are some things which you should know at that level. This is the picture of a famous elephant in Kerala, and let us look at a beautiful elephant. Do you think it's a beautiful elephant? Or an elegant elephant? Let's beautify the elephant. Now the elephant looks very beautiful. This is an infrared image of the elephant. So the point here is infrared. We are not using visible light to get this picture, but this is when you look through an infrared camera. The colors are artificial. This is color coded. Color means temperature, as you can see here. Blue color is cold and red means hot. That's what it means. So it's a color-coded signal. Infrared you cannot see, so you cannot really see an infrared picture. So after color coding, you can see. This shows which are the hotter part. It's breathing air, taking or exhaling air. So this part is red, and the ear part is cool and gets cool. So this is a lot of information biologists get from this picture. So when you look at a different wavelength, other than the visible light, you get different kinds of information. Of course, when you look through the visible colors, you see a lot of information. So what happens when light interacts with matter? You can imagine what would happen when Maradona visited Kerala. Suppose he came in. What will happen to the crowd when he enters the hall? The crowd will start getting excited. The crowd will start dancing. And that's what we are going to talk about. When light enters matter, what happens to the molecules? The molecules start dancing. And it is the dance of the molecules, as I was mentioning earlier also, that gives us a lot of information. The rhythm of molecular vibration. That is what Raman has brought to notice. Okay, what happens when a photon enters? Here we will look at the wave picture of light. Light meets matter. So light consists of an electromagnetic wave. So you have an electric field. Light has an electric field and magnetic field. The effect of magnetic field is not much because it is much weaker than the electric field. So let us look at, one second. Let us look at the effect of the electric field on matter. Now, what does matter consist of? Light consists of an electric field. It's jumping up and down. At what frequency? 10 power 14, 10 power 15 times a second. That's what comes in. And what is there inside matter? I will talk about this later. What is inside matter? Matter consists of dipoles. Plus and minus. Matter is made up of charged particles. So you have plus and minus. They are equal in number in neutral matter. But then the plus and minus are situated at some distance. So you get a dipole. Polar, many molecules are polar. Water molecule is polar, you would have seen. But what about oxygen molecule? It is not polar. But then when light interacts with even a non-polar molecule, it polarizes. Light can separate the plus and minus. So light has, because we have an electric field, and these are charged particles. The plus charge part and the negative charge part can get separated, polarization. So polarization can be induced by an electric field. So temporarily you can generate molecules. Molecules vibrate. So the molecular vibration can be affected when light interacts with molecules. And that can result in shift in frequencies. This is the original frequency omega naught, and you can get a higher frequency and a lower frequency. Or you can get a shorter wavelength and a longer wavelength correspondingly. That is a summary of Raman effect. In short, when light interacts with matter, the molecular vibrations in matter get altered, and what you get is light of different frequencies. as opposed to Rayleigh scattering, the normal ordinary scattering, when the color doesn't change. Just imagine if color happened to change in Rayleigh scattering. Then if I come with a blue shirt, you will see me in a red shirt because it scatters and changes the color. No, it doesn't happen. In ordinary scattering, normal scattering, which is called Rayleigh scattering, the color change doesn't happen. The photon is elastic. It's not, it just does something and comes out. That's what happens. But energy is not absorbed by the molecule or energy is not given. But on the other hand, in a different process, which is a Raman scattering process, there you get frequencies, higher frequencies and lower frequencies. We will look at it deeper. This is just a summary of what Raman effect is. As I mentioned, the electric field, what is incident is an electric field which is varying at a frequency 10 power 14, 15 when you're talking visible light. And it polarizes matter. Some form of matter like water molecule are already dipolar. Otherwise, you can induce dipoles in matter because the plus and minus can be separated by electric field. That's called polarization. This can be described quantitatively by talking about defining a dipole moment. Dipole moment is charge into distance. That's you know from elementary physics. The dipole moment can be defined. This is in one dimension. I have ignored the vector nature of it. Now, what happens when a particular molecule is under the influence of electric field which has different intensity? At some small intensity, the effect is not much. But if the intensity is larger and larger, intensity is the square of amplitude. So if the amplitude of light is larger and larger, the electric field is larger and larger, you get more of this pushing apart, which is called polarization or dipole. We'll get more and more dipole moment. This is described quantitatively by a quantity called polarizability. So I have here two quantities. The first one is the definition of a dipole moment, the charge and the distance, just like a short magnet, for example. So this is dipole moment, and this is polarizability. Polarizability describes a different aspect. It describes how much dipole moment is generated per unit electric field. If the electric field is larger and larger, you get more and more dipole moment. This is what this equation describes. These two quantities are very important for us to understand the whole thing. So let us get a clear idea about what is polarizability and what is the dipole moment to start with. Now, the oscillating dipole. What happens to an oscillating dipole? Why does the dipole? There are three things. First, there is dipole. There is molecules like water has a dipole moment, or the light can induce the dipole. That is first. Secondly, this is under the influence of the alternating electric field which comes from the light, which means this oscillate. The dipole can oscillate. And when dipoles oscillate according to classical physics, you can have emission, okay, radiation, and that radiation comes at the same frequency as the incident wave. This is the first principle to understand. An oscillating dipole, there is a quantum classical picture of this process of emission. So this is how you see light Rayleigh scattering. How do you describe the molecular dance, molecular vibration? Look at the potential. The potential curve, the potential experience. This is a very simplified model. We just have two atoms are stuck together, and the equilibrium position is what is the origin of the X, and the separation is described by X. Momentary X is a function of time. At any time, how much it is far away from the equilibrium position, that is X. And potential changes, and this is the potential. So now potential has a complicated shape. So you can describe it using a Taylor series expansion. The potential is equal to the first approximation. At the zeroth approximation, the potential is exactly equal to the potential at the mid equilibrium position. And then you have the first derivative into separation. Then you have the 2 factorial, 1 by 2 factorial, second derivative, the square of the displacement. It goes on like that. But we simplify the whole picture. by first taking an origin in such a way that this is the constant potential. Constant potential doesn't mean anything. It's only the potential difference which makes anything, which means anything. So let's keep our origin here so that you don't have the first term. And then you ignore the higher terms. These higher terms you ignore. Then finally you are left with just two terms. And this is what is written as the spring force, or the spring potential half kx squared. Okay, this is how it comes. And can anybody tell me who is this? Who this is? This picture, audience? What is this picture doing here? Who could it be? I will give clue. See, nowadays you ask for clue. Whenever you are asked a question, you want some clue. This is happening inside a church. And this is happening long back, several hundreds of years back. And this has to do with vibration, pendulum. And what you see here, this object is swinging pendulum.
This focal pendulum.
Focal? Oh, you are going overboard. You are going away. I mean, more than what I am asking. The answer is overqualified. It is not even a pendulum. It's a crude pendulum. It's a lamp in the church. It happened to be oscillating. You want another clue? This side doesn't have a watch. How does he measure time? He's feeling his pulse.
Sir, is that Galileo?
What did you say?
Galileo.
Galileo. This is Galileo in a church. Galileo was there in a church and he happened to notice that a chandelier is swinging. And then he suddenly made some observations about the pendulum oscillation. And he has to measure time, how much time it takes each journey of the bob of the pendulum. And he didn't have a watch, so he was looking at the pulse and measuring. He is the one who made the first theory of all this. So we shouldn't forget that. Okay, so molecules vibrate. The vibration, let's take a very simple picture and let us take it like this. A cos function which describes omega is the frequency at which it vibrates. Now omega, is given by this k I have already defined. This effective mass which comes into picture. Okay, and this is a simple picture of a molecule. It's a little more complicated than the pendulum. In the case of pendulum, there is only one mass, which is the bob. Here there are two masses, so we have to consider the effective mass of that. Let's look at a molecule, carbon dioxide molecule. Carbon dioxide molecule can vibrate in different ways. In some of the vibrational modes, these are called the vibrational modes. It can bend, it can vibrate like that, it can vibrate like this, breathing mode, it can vibrate in different ways. I will have a picture later. So let us look at this vibration. And see, carbon and oxygen comes towards the carbon and this oxygen goes away. Then in this particular vibration, what happens in this particular vibration? Dipole moment does not change. Dipole moment may change or may not change in a particular vibration. We will see more pictures later. When the dipole moment doesn't change, there is nothing happening. But if the dipole moment changes, that is the derivative with respect to q. Q is a coordinate. Here, I earlier used as charge, but q is a coordinate, d by dx. So when it moves as a function of the distance moved, the dipole moment does not change, then it will absorb infrared radiation. This is in fact the condition for absorbing infrared. Why am I talking about infrared suddenly? Because molecular vibration happens in infrared. The difference between the quantized levels of molecular vibration correspond to the infrared quantum energy of the infrared light. The electronic transition, the difference between the levels of the electronic transition corresponds to visible light. That's how you all this various atomic spectral lines and all that. You also know that the rotational energy is also quantized, and the difference in the rotational levels correspond to microwave. That is how you have the microwave oven. Now coming back to the present context, the molecular vibration is also quantized, and it can happen in E1, E2, E3, like the quantized energy levels. And the difference between these quanta, these levels, corresponds to the quantum energy of infrared region. That's what's called infrared absorption. It's just like light absorption. Only thing is here the process is molecular vibration. Infrared absorption is described by this. If you want to have infrared absorption, then the dipole moment should change during the vibration. If the vibration doesn't permit this to change, you don't have infrared vibration. Now what about Raman? This is called this, what I said just now is called the selection rule for infrared vibration. Now Raman also addresses molecules. It's about molecular vibration. So the other infrared absorption is one technique to understand, or one phenomenon which is happening, which can be used as a spectroscopic technique to probe them. The next one is this, that is the Raman, again in molecular vibration. But what is the difference? Here we are talking about the dipole moment. The dipole moment should change. And when you come to Raman, the selection rule is different. What you have is the polarizability. The polarizability can change. In some mode of vibration, the polarizability changes. In some other mode, doesn't change. Again, I will show the specific example. Omega y is a vibrational frequency of molecule. This is the frequency at which a particular molecule vibrates. Now, in this case, in general, different ways of vibration. In a particular way of vibration, here the oxygens are going away from the carbon. Oxygens are going up and down, away from the carbon. So the polarizability is actually pictured by an ellipsoid, polarizability ellipsoid. It just tells you the extent of polarizability. So polarizability, if the polarizability is different before vibration and after vibration, I mean in the different equilibrium state and non-equilibrium state, then we can describe polarizability by this equation. Again, a Taylor series expansion, polarizability alpha. This is the polarizability of the molecule, it's a property of the molecule. That is alpha naught, some quantity, plus dr, that's corresponding to equilibrium, and then d alpha by dq into q, q1 minus q2. This is the, we ignore all the other terms of the Taylor series. Now, we have alpha, we have defined alpha, and we have also defined alpha in terms of p, this equation. So we put that into this equation, and we can write P as alpha naught T plus d alpha by dq QE. E is electric field. Please note Q. So okay, Q here is okay. Here Q is a distance. Now both this, all this put together. Now we'll put all this into this equation and write an expression for the dipole moment. When you write an expression for the dipole moment, incorporating this, remember this is an approximation. We have ignored the higher the terms of the Taylor series expansion. So we see that the output contains three frequencies. First frequency is omega naught. That is the frequency of the incident light. And this phenomenon, this part of the story is Rayleigh scattering. That is, what is happening here? There is an incident light. Incident light shakes the molecules. And the molecule, because they are radiating, they are accelerating, they have to radiate, and in that process they radiate. They radiate three kinds of light. The first one is Rayleigh scattering without any change in the frequency. Now there are two more appearing. One at a lower frequency, which is a longer wavelength, red part of the spectrum, and the other one is the higher frequency, which means the blue part of the spectrum in wavelength. This you can show mathematically. I'm not showing all the steps, but this is any elementary book on Raman effect. So you just see that there are two things which I want to show. First, an analysis putting this together will give you three terms, three output frequencies: original frequency, the lower frequency, and the higher frequency. That's the first thing I would like to mention. And the second thing I want to mention is to request you to have a deeper look at the quantities. Look at this quantity, the second term. Ask the question, when will I see a different frequency? When do I see a different frequency? What is the condition that I should see a different frequency also? Original frequency is anyway present, but difference, these two terms will not be there present all the time. What is the condition that these terms must be present? Anyone? A clue is what I did for the selection rule for the infrared. So we also have a selection rule here. What happens?
What?
Look at the
Polarizability
purely
should-
mathematically. Under what condition will you see strokes or anti-strokes? Or under what condition these two disappear? Look at this. What happens if this is 0? If this bracketed quantity is 0, then you will not see the strokes and anti-strokes line. No Raman effect. You will see only the original frequency. Okay, so this is what happens. That is the selection rule for Raman. Why I'm mentioning this is generally people find it difficult to remember and to confuse, they get confused with the selection rule for infrared and selection rule for Raman. And when you come for an interview, people ask these questions. Oh, you have done molecular physics, you have done spectroscopy. Tell me why the infrared, what is the kind of selection rule for infrared, selection rule for Raman. People get confused. That's why I presented in a simple manner. And the equations can be seen in any book anyway. So to repeat in this part, you have 3 frequencies appearing here, which means the original light, which is Rayleigh scattering, and then you get light at a different frequency also coming out of there. And what is the condition? Not always. When I look at you, I don't see a different color. This condition should be satisfied. That particular molecule should vibrate first, and when they vibrate, the alpha should change with Q. Q is this coordinate of vibration, how much it vibrates. So when it vibrates, the alpha should change. If that particular mode of vibration does not permit it, you don't see that in Raman spectrum. So this is the selection rule for a Raman transition. For a transition to occur in which you get some energy from the molecule or give some energy to the molecule and get a different color of light out, the condition is this. This is called selection rule for Raman. The polarizability, the derivative of the polarizability with the vibration, d alpha by dq, should be non-zero. Then you have Raman effect. To compare, the selection rule for infrared we just mentioned earlier, that the dipole moment should change. Here the polarizability should change. Doesn't matter what happens to dipole moment. This is the selection rule for Raman. And that is how all these 3 frequencies come in. This is very useful. Now molecules are complicated. We were talking about simple diatomic molecules or carbon dioxide, which is one more item. But molecules are very complicated. You know, in organic chemistry, there are very complicated molecules. They can vibrate, they can do breakdance. Parts of it can vibrate. And the molecules vibrate in different ways. Some of them change polarizability during vibration. Some of them change, some modes, same molecule. Some modes may change dipole moment. Some modes may not change. Some mode may change polarizability. Some may not. So it looks like very complicated. But there is a beautiful principle. If the molecule has got inversion symmetry, that is center of symmetry. If the molecule is symmetric with respect to center, in 1 dimension, same thing is sitting this side of the center, that side of the center. In 2 dimension, plus x1, y1, minus x1, y minus y1, there is the same molecule, same kind of molecule sitting. Then you have in 2 dimensional symmetry. In 3 dimension, it means whatever molecule is sitting at the distance plus x1, plus y1, plus z1, the same kind of molecule is sitting at minus x1, minus z1, minus y1. Then you say it is symmetric. There are symmetric molecules like oxygen. There are, as in most of the other molecules, are not symmetric. So in the case of symmetric molecules, the modes which show Raman effect do not show infrared. And the modes of vibration which show infrared do not show Raman. This is called a mutual exclusion principle. So what is the easy method now to find whether a molecule has a center of symmetry? Take the infrared spectrum, go to the other lab and take the Raman spectrum and compare. Then you see that they are mutually exclusive. Then you can see decide that the molecule has got a center of symmetry. This is very useful in predicting the shape, the structure of molecules in early chemistry. Let's look at the processes. What we have seen just now is that if the conditions are favorable, if the selection rules are met, then you have incident light lambda 0 wavelength and emitted light at different wavelengths. The same wavelength at longer wavelength and shorter wavelength. Let's see what happens. These are the molecular energy levels. These three are the molecular energy levels. Some basic level, upper level, lower level. And molecules are initially in this state, let's see. These are virtual levels. This is only pictorial representation of Raman effect. So these are virtual levels. For convenience, we are imagining them. The real levels are here. This process which you see right now is called optical absorption. Optical or infrared or whatever. Some quantum comes in. If E2 minus E1 is equal to the H2, then it absorbs. So let us say it absorbs and goes to this level. The molecule here. What can happen to it? It will have a finite lifetime there and then it will come back to the same level. What happens when it comes back to the same level? It emits the photon. And the absorbed photon and the emitted photon will have the same quantum energy, or the wavelength will exactly be the same. This process is called the Rayleigh scattering, which all of us know very well. This is what is happening in daily life. This is what happens when you look at anything in the world. When you look at it, your eye is catching the same wavelength, which is, of course, when you look at a colored object, there are all visual falling on it. Some of them are absorbed. But whatever red was falling on it, and if that red is coming out, there is no other than lambda. Because energy is shorter. This is the energy scale. Please remember this is an energy scale, y-axis. So you have shorter energy for this. Red one is shorter in energy than the blue one. Blue one is the exciting one. So this has got a longer wavelength, shorter energy. Some energy is given to the molecule. And that is called the Stokes Raman. And then you have the other possibility. Now you can guess the other possibility. You can go to another level below that. So what happens here? The wavelength will be shorter, then the energy will be more, and wavelength will be short. This is the light which is emitted. So the molecule gives content of energy, and what you get is a higher energy light, which means shorter wavelength light. And this is called anti-Stokes line. That is how you have the three lines. That is what you see in a spectrum, the Rayleigh, the Stokes and the anti-Stokes. Stokes are much easier to see because there it is to the ground, above the ground state it happens. And here it has to come to a state which is even less. So by population Maxwell's Boltzmann, the distribution, you know that ground states are always highly populated. So that reason it's generally difficult to see the anti-Stokes line. So this is how you see three different colors. This energy diagram explains the phenomenon which you see here. As I promised, we will have a look at how molecules vibrate. There are three basic modes. These are called the normal modes. And any other modes they vibrate are linear combinations of these normal modes. So the basic normal modes of vibration for carbon dioxide and corresponding the alpha polarizability picture is what is shown here. This is called symmetric stretch. Both the O's go up and down from C. And the second one is called asymmetric stretch. One side it is more, the distance between one carbon and oxygen becomes more or less than the other one, if you see clearly. And then there is a bending mode, which I am not showing here. And water molecule, whatever water molecule does in all possible things, this picture changes here, alters. Now, if you plot alpha as a function of Q, this I should have used small q. Q means the distance. And alpha is polarizability. If you plot alpha as a function of the distance, that is while the molecule is vibrating, then you see that in this case, d alpha, if the picture is like this, the first case, then you have d alpha by dq non-zero. Whereas in the other two cases, it is d alpha by dq 0. So in these antisymmetric and bending modes, you don't have change in this. So Raman frequency doesn't see those vibrations. It sees only the symmetric stretch in the case of carbon dioxide. Similarly, you can write it for all molecules and then you can see what it is. Now, the selection rule for carbon dioxide. See the first case, it is the size which changes. Size of the polarizability ellipsoid changes. In the second case, it's the shape which changes. So depending upon that, this mode is Raman active or Raman inactive. Okay, that is how we can explain the Raman phenomena in this. Similarly for water molecule. In the case of water molecule, all the vibrations are Raman active. Carbon dioxide, if you remember, carbon dioxide is a symmetric molecule, so there is a mutual exclusion. Whatever is Raman active is not IR active, and whatever is IR active is not Raman active. That you can quantitatively predict using this. Here you see the typical Raman spectra of some molecules. So the chemists look at this, okay, the CO bond or CH3 molecule has got a signature like this. The CO bond always appears, the vibration of CO bond always shows at this particular number. Wave number, this is measured in wave number, centimeter units, 1 by lambda unit, that kind of units. So you can, looking at that, immediately they will be able to tell you, okay, there is a C double bond in this. Or there is a particular, or if you see a pattern, okay, this is the photograph of CH3, that they will be able to tell you. That's how you, not only that. So this is the kind of thing, this what we are talking about, this is from Cochin University, a public website of Cochin University. This actually shows the Raman effect. You can see the light, the green one, green light has changed into red light. So you see the green and the red. The green is filtered off so that you see only the red. So this is actually a picture showing the demonstration of Raman effect. In this case, you cannot see the anti-strokes because it is weak. Now the point is, Raman effect is not just a discovery, just one single discovery. It is not that. It is beyond that. Raman discovery, Raman effect has grown beyond. It's a true noble work. Its impact grows even today it is relevant. It doesn't decay after a few years after getting the Nobel Prize or something like that. Often Nobel Prizes are awarded much later, several years after the discovery, whereas in this case there was not much gap between these two. Now, why does this picture show? Why does this picture show horses, cars and horses? I'm not giving a lecture on cars and horses. I'm giving a lecture on Raman. Cars is coherent anti-Stokes Raman, and horses talks about higher order Raman effect. And stimulated SRS is stimulated. Photoacoustic Raman is photoacoustic Raman scattering, and surface enhanced. So this I'm talking about the growth of Raman from the basic simple experiment which we discussed. It has gone to a very high level of sophistication today, and you can see. Just an example from a picture to show what kind of instruments. It is used in pharmaceuticals, biological, life sciences, polymers, technology, polymer technology, carbon nanotubes, material science, semiconductors. Raman, that simple experiment which you saw, is used to characterize such a lot of mineralogy, chemical industry, electrochemistry, archaeology, environment. Everywhere this is important. A piece of interesting work. This we had published in 2011. What you see here is the Raman spectra of graphite and graphene. Graphite, different layers like that. So what you see is that the D band is a typical band which you see in this. And then 2D band happens, and then there is a G band. These are specific origins and all that. You have to read the paper to understand why they are. But they are characteristics. The point is they are characteristics of graphene. And what is interesting in this happen. Characteristic means each of them happens because of some vibration in graphene. And interestingly, as graphite becomes graphene, graphene is monolayer. Graphite several layers. So if it is several layers, you get a spectrum like that. And if it is more than 3 layers, you get it like this, bilayer like this, monolayer like this. So there is these things do not change, but here there is a systematic change. So once you have a layer, you can immediately look at it and tell you whether it is single layer or double layer or multi-layer or it's bulk graphite. You can easily say using Raman. Just take the Raman spectrum, immediately you know whether you have made it successfully. And finally, in the last few minutes, I would like to talk to you about the Raman laser. To understand the Raman laser, first we have to understand the random material. Look at this object. This is the one particular insect. It's called Siphoculus beetle. People examined the white color of its wing, and they found that there is a random structure. I don't know whether the word random structure is correct. If there is a structure, it is not random. Okay? So a lot of interesting optical phenomena happens when a medium is random, irregular medium. And people say it has got a huge research potential. What is meant by random? This is a random maze. You don't know where the next way is going to lead you. It's like life. Anything in life, such things happen in life. Nobody predicted that 2020, this is kind of life we are all going to lead. So this is life itself is random. But what happens when light enters a random environment? A random environment is where particles are kept randomly without any regular order, and light travels through that. Our body is a random medium. It's full of randomly positioned particles. And what you see is luminescence like this. Oh, I suddenly see that I have crossed 11, but I'll take about maybe I think less than 10 minutes I'll take. Before that, I have to send a message because 11 o'clock I'm supposed to do something else. I will just excuse me for it. It is important. You can have a good look at this. What happens? Hello, I am in a meeting, so I will come after some 10 15 minutes. Then you can so either postpone the letter or you talk with other students, and then before she comes, I will. Okay. Okay. Yeah, it's only empty. Okay. It gets I thought it will be over by 11 o'clock. Yeah. So this is what happens. And we are interested in it because we are made up of random media. When something goes bad in our body, how we can use this knowledge to get information out of it. There is multiple scattering scenario. In general, when light goes through a medium which is scattering, it just gets scattered by randomly positioned particles, and it comes out of some direction. But there are some scenario you can arrange matters which I will give you some reference, you can read that. And then you can have interesting scenario happening in the medium. And this is the reference. This reference is very good. You can read that, and that will tell you about the fascinating physics of light meets matter. Light meets random matter. What happens? We will come to the relevance to Raman shortly. So the possible applications of this is in biological, this branch of science, which deals with light meeting randomly positioned, random matter, randomly structured matter. So a lot of applications are foreseen for this. Now I'll talk about a simple experiment. This simple experiment, there are two materials here. What you are looking at is the luminescence spectrum of two materials. One is zinc sulfide. Zinc sulfide has a luminescence around 560 nanometer, green light it emits. And then you have a dye which is beta carotene. Beta carotene is a natural substance which is there in carrots and many other objects. So this is beta carotene. Beta carotene emits at the same wavelength as zinc sulfide. So what happens when you make a random medium of zinc sulfide? There are techniques for that. You can see this reference for that. You make a random medium of zinc sulfide and then pour this liquid, the beta carotene into it. And then again you get the emission. But the emission that you get out of this is totally different from 1 and 2. It is totally different. And what you see is this kind of very sharp, highly intense and very sharp emission, which is actually a laser emission. This is the Raman laser. This is the principle of the Raman laser because this happens to be the Raman bands of this, the Raman emission, Raman modes of this molecule. Each molecule vibrates in a particular way, and you have the Raman mode when the polarizability changes. That's what we have seen. And this is an example of that, an illustration of that. This beta carotene is a complicated molecule. It emits at 527 nanometer and some 517 nanometer. These are the vibrational modes of that. And you see, when you put it in a random medium, what you see is the laser. See the difference between fluorescence, ordinary fluorescence, and laser. In the case of ordinary fluorescence, it spans over several wavelengths and it is not very intense. Whereas once you make a laser out of it, look at the numbers on the y-axis. This is hundreds. So it is weak and it is broad, but it becomes highly intense and it becomes very slim, very narrow. So it becomes a laser. This is called this is the principle of the Raman laser. Lasing happens at the Raman frequencies of the material. So these details can be seen, but the theory cannot be explained very easily. It depends on the energy levels of carotene and the Raman effect happening there and all that. You can, those who are interested can note down this quickly, and then that describes all that. How the chemicals are prepared, how the medium is prepared, how the Raman spectrum is taken, and how it is analyzed. This shows this points to the way of designing a new kind of laser. This is called the Raman laser. And this is, for example, you can take carrot. Actually, you don't need zinc sulfide. You can just use carrot alone. What do you need for a laser? You need a source of light. You need something which gives you light, laser light. When it is pumped with optical pumping, for example, then the outcome is a laser. That kind of medium you want. Here the medium is beta carotene. And then if you want the Raman lasing to occur, you can put it in a random medium and make this random scattering possible. And when the Raman scattering is made possible, so for that, first we use the zinc sulfide. But then we found that why do you use zinc sulfide? You don't need zinc sulfide. The carrot itself has a structure, random structure, cellulose structure. So the random scattering events in the cellulose structure itself gives you local cavities for laser action, for amplification of the spontaneous emission, as a stimulated emission. And the stimulated emission comes from beta carotene. So this is the bio-friendly carrot laser which we developed. Now, coming back to what I was trying to show you is to tell you about the basics of light scattering and light matter interaction, and then come to two important concepts: the dipole moment and polarizability, and how they are important in Raman scattering, the basic principle of Raman scattering. And then I quickly jump to several examples of Raman scattering, what Raman can do, Raman spectrum can do today, how it has grown. But at the heart of all that is the basic philosophy of Sir C.V. Raman. This is a quote from the book which the talk which I was mentioning, and that is what you have to take home. The essentials of scientific spirit is the essence of the scientific spirit is to look behind and to look beyond. Everything that we see, I think this quote I mentioned earlier, is a challenge to the spirit of the man to try to understand the vast mystery that is surrounding us. And that is the spirit of Raman. And the vast mystery is surrounding us everywhere, even inside and outside, and inside the heart of the molecules. And that is what Raman demonstrated, actually, in Raman effect. You see a little, this is the quote which I mentioned earlier. Even that little is enough to elevate the human soul, to realize what a wonderful world that we live in. The best way to conclude this lecture will be this. പണ്ടൊക്കെ കേരളത്തിലെ മുത്തശ്ശിമാരെല്ലാം കുട്ടികളെ മടിയനായി നിൽക്കുമ്പോൾ പറയും, അവരെയൊക്കെ ചീത്ത പറയാറുണ്ട്. നിങ്ങൾക്ക് വേറെ പണിയൊന്നുമില്ലെങ്കിൽ ആകാശത്ത് നോക്കി രാമരാമ ജപിക്കാൻ പറയും. നിങ്ങൾക്ക് വേറെ പണിയൊന്നുമില്ലെങ്കിൽ ആകാശത്ത് നോക്കി രാമരാമ ജപിച്ചുകൂടി. So that is what we can do. Even we can do a lot by that. We can look at the sky and imagine Raman effect, what is happening there, and take inspiration from what Raman did, how Raman interpreted the color of various objects, the molecules, and what are the applications of Raman effect. That's the message which I like to part with. And what you see here is, of course, the blue sky and Raman. And this photo is taken from the Raman Research Institute. You can ask more to the next speaker, Reggie Philip. He comes from Raman Research Institute. And Raman Research Institute has got a tree there. It has got many trees, but a particular tree has very great importance. This is where Raman's physical remnants were kept. So that is the importance of this tree. This is the reminiscence of Raman. This in remembrance of Sir C.V. Raman, his work, his inspiration, this tree has been planted in Raman Research Institute. So you can ask Reggie about that when he comes. Thank you. The purpose of my talk was, as I mentioned, first to tell you about some aspects of light which are important for Raman effect. And secondly, some aspects of matter, which is the dipole moment and the polarizability, which lies at the very heart of Raman effect. And then I wanted to convey to you something about what Raman effect can do to molecules, to substances as graphene and all that. And finally, the basic idea of a Raman laser, how a Raman laser can be developed in a very nice, efficient manner. I hope you have got the message on these things at some level. And please do look at the references, especially the talk, Raman's talk, which is an unforgettable piece of reading. I can guarantee you that much, which will inspire you. If it can inspire me at this age, definitely it can inspire all of you. Thank you. If there are some questions and clarification, I can take that. You can unmute both audio and video and ask. മലയാളത്തിൽ ചോദിച്ചാലും മതി.
സാർ ലൈറ്റ് ഇൻഫർമേഷൻ ക്യാരി ചെയ്യുന്നു സാർ പറഞ്ഞു. നമുക്ക് കിട്ടുന്ന റാൻഡം ആയിട്ടുള്ള നോയ്സിലും ഇൻഫർമേഷൻ അടങ്ങിയിട്ടുണ്ടോ?
റാൻഡം ആയിട്ടുള്ള നോയ്സിൽ ഇൻഫർമേഷൻ ഉണ്ടെങ്കിൽ എന്ന് ചോദിച്ചാൽ ഈ റാൻഡംനെസ് വരുന്നത് പലതരം ഇൻഫർമേഷൻ കൂടിയിട്ടാണ്. ഇപ്പോ ഒരു ക്ലാസ്സില് ടീച്ചർ സംസാരിക്കും, മറ്റുള്ളവർ കേട്ടിരിക്കുകയാണെങ്കിൽ അവർക്ക് അത് മനസ്സിലാക്കാൻ പറ്റും. പക്ഷെ എല്ലാവരും സംസാരിക്കാൻ തുടങ്ങി കഴിഞ്ഞാൽ ഓരോരുത്തരും അവരുടെ നൈബറോട് പറയുന്നത് ഒരു പ്രധാനപ്പെട്ട കാര്യമാണ്, വളരെ ഇമ്പോർട്ടൻറ്റ് സിഗ്നലാണ്. പക്ഷെ കുറെ സിഗ്നൽ ഒന്നിച്ച് ഒരേ സമയത്ത് വന്നു കഴിഞ്ഞാൽ അത് നോയ്സ് ആവും. സോ what you call as random is also made up of lot of maybe meaningful single things, single frequencies. So information അടങ്ങിയിട്ടുള്ള too much of information ഫേസ് തമ്മിൽ ഇൻ ഫേസ് അല്ലാത്തത് കൊണ്ട് അത് ഓവറോൾ അതിൽ നിന്ന് ഡിഗപ്പ് ചെയ്യാനായിട്ട് വിഷമമാണ്.
ഓക്കെ സർ.
സർ ഒരു ഗ്ലാസ് വെള്ളം എടുത്തു കഴിഞ്ഞാൽ അതെന്തുകൊണ്ടാണ് ട്രാൻസ്പെറന്റ് ആയിട്ടിരിക്കുന്നത്?
ഒരു ഗ്ലാസ് വെള്ളം എന്തുകൊണ്ട് ട്രാൻസ്പെറന്റ് ആയിട്ടിരിക്കുന്നത്? അതില് അബ്സോർബ് ചെയ്യുന്ന ലൈറ്റിനെ അബ്സോർബ് ചെയ്യുന്നതായിട്ടുള്ള മെക്കാനിസം ഒന്നും ഇല്ലാത്തതുകൊണ്ട്.
സർ അപ്പോ
സോഡിയം ക്ലോറൈഡ് ക്രിസ്റ്റല്, അത് കുറച്ചുകൂടി എളുപ്പമാണ് മനസ്സിലാക്കാൻ. വെള്ളം ആക്ച്വലി വളരെ വിഷമം. വെള്ളം എന്ന് പറഞ്ഞാൽ പച്ചവെള്ളം പോലെ സിമ്പിൾ ഒന്നുമല്ല, അത് കുറെ ബുദ്ധിമുട്ടുണ്ട് മനസ്സിലാക്കാൻ. ഓക്കെ, ഫസ്റ്റ് നമുക്കൊരു ക്രിസ്റ്റലിന്റെ കാര്യം എടുക്കാം. സോഡിയം ക്ലോറൈഡ് ക്രിസ്റ്റല്, സോഡിയം ക്ലോറൈഡിന്റെ ഐഡിയൽ ക്രിസ്റ്റൽ, നോട്ട് ദി നമ്മൾ ഉപ്പ് വാങ്ങുമ്പോൾ കിട്ടുന്നത് അല്ല, അത് പല പീസായിട്ട് പൊടിഞ്ഞതാണ്. ഒരു ഐഡിയൽ സോഡിയം ക്ലോറൈഡ് ക്രിസ്റ്റൽ എടുത്തു കഴിഞ്ഞാൽ അത് ട്രാൻസ്പെറന്റ് ആയിരിക്കും. അതിന് കാരണം എന്താണെന്ന് വെച്ചാൽ ബാൻഡുകളിലാണ് എനർജികളെല്ലാം ഉള്ളത്. എനർജിക്ക് ഏത് വാല്യൂ എടുക്കാൻ പറ്റില്ല. അപ്പൊ കണ്ടക്ഷൻ ബാൻഡിനും വാലൻസ് ബാൻഡിനും ഇടയിലുള്ള ആ റീജിയൻ ആണ് ഇപ്പൊ വിസിബിൾ ലൈറ്റിന്റെ ക്വാണ്ടം എന്ന് പറയുമ്പോൾ അറൌണ്ട് 2 to 3. അത് ഇപ്പൊ ഗ്രീൻ ലൈറ്റ് ആണെങ്കിൽ 2.5 ഇലക്ട്രോൺ വോൾട്ട്. 2 to 3 ഇലക്ട്രോൺ വോൾട്ട് ആണ് വിസിബിൾ ക്വാണ്ടം. അപ്പൊ ആ വിസിബിൾ ക്വാണ്ടത്തിന് ഇതിൽ ഒരു ലെവലിൽ നിന്ന്, ഒരു ബാൻഡിൽ നിന്ന് മറ്റു ബാൻഡിലേക്ക് ഇലക്ട്രോണിനെ എക്സൈറ്റ് ചെയ്യാൻ കഴിയില്ല. അതുകൊണ്ട് ഒന്നും സംഭവിക്കുന്നില്ല. എന്ന് വെച്ചാൽ ലൈറ്റ് അങ്ങനെ അതേപോലെ കടന്നു പോകുന്നു. അത് വളരെ എളുപ്പമാണ് മനസ്സിലാക്കാൻ. വെള്ളത്തിനെ സംബന്ധിച്ചോളം എങ്ങനെ പറയാം, വെള്ളം ഒരു മോളിക്കുലർ സബ്സ്റ്റൻസ്, ക്രിസ്റ്റൽ അല്ല. അപ്പൊ ഈ മോളിക്യൂളുകളുടെ ചലനത്തിന് ഈ വിസിബിൾ ലൈറ്റിനെ അബ്സോർബ് ചെയ്യാനായിട്ടുള്ള മെക്കാനിസങ്ങൾ ഒന്നുമില്ല. അതിനൊരു എനർജി മെക്കാനിസം ആണല്ലോ. ഫോർ എക്സാമ്പിൾ, വെള്ളത്തിന് വേറൊരു കഴിവുണ്ട്. വെള്ളത്തിന് ഡൈപോൾ മൂവ്മെന്റ്, ഹൈ ഡൈപോൾ മൂവ്മെന്റ് ഉണ്ട്. അപ്പൊ വെള്ളത്തിന് വാട്ടർ മോളിക്യൂൾസ് റൊട്ടേറ്റ് ചെയ്യുന്ന സമയത്ത് ഡിഫറെന്റ് ക്വാണ്ടൈസ് റൊട്ടേഷണൽ എനർജി ലെവൽസ് ഉണ്ട്. അപ്പൊ ഇതിൽ ഒരു എനർജി ലെവലിൽ നിന്ന് മറ്റൊരു എനർജി ലെവലിലേക്ക് പോകണമെങ്കിൽ ഇൻഫ്രാറെഡ് ആണ് അതിന്റെ ഡിഫറൻസ് ഈക്വൽ ടു. അതുകൊണ്ട് ഒരു ഇൻഫ്രാറെഡ് ക്വാണ്ടം, മൈക്രോവേവ് ഒരു മൈക്രോവേവ് ക്വാണ്ടം വരികയാണെങ്കിൽ അതിനെ അബ്സോർബ് ചെയ്തിട്ട് വാട്ടർ മോളിക്യൂളിൽ കൂടുതൽ റൊട്ടേറ്റ് ചെയ്യാൻ പറ്റും. അതുകൊണ്ടാണ് നമ്മൾ മൈക്രോവേവ് ഓവൻ ഒരു ഹീറ്റർ ആയിട്ട് ഉപയോഗിക്കുന്നത്. അപ്പൊ അൾട്രാ വയലറ്റിന്റെ ക്വാണ്ടം എനർജി മൈക്രോവേവിനേക്കാളും വളരെ കൂടുതലാണ്. അറിയാമല്ലോ, അൾട്രാ വയലറ്റിന്റെ വേവ് ലെങ്ത് വളരെ കുറവാണ്, എനർജി വളരെ കൂടുതലാണ് മൈക്രോവേവ്. പക്ഷേ അൾട്രാ വയലറ്റിനോട് ഒരു ഓവൻ ഉണ്ടാക്കി കഴിഞ്ഞാൽ നമുക്ക് വെള്ളം തിളക്കില്ല. വെള്ളം തിളക്കണമെങ്കിൽ വെള്ളത്തിന്റെ മോളിക്യൂൾസിന് പറയാം. ഇപ്പൊ ചെറിയ കുട്ടിക്ക് അതവർ കിടക്കുകയാണെങ്കിൽ ആ കുട്ടിയുടെ ഭാഷയിൽ സംസാരിക്കണം. അതേപോലെ വെള്ളത്തിന് വെള്ളത്തിന്റെ മോളിക്യൂളിനെ ഹയർ ലെവലിൽ റൊട്ടേറ്റ് ചെയ്യണമെങ്കിൽ അത് തമ്മിലുള്ള ക്വാണ്ടം എനർജിക്ക് തുല്യമായിട്ടുള്ള എനർജി കൊടുക്കണം. അത് മൈക്രോവേവിന് മാത്രമേ സാധിക്കൂ. അപ്പൊ മൈക്രോവേവ് ആണ് വെള്ളത്തിൽ കൂടെ കടന്നു പോകുന്നെങ്കിൽ ഇങ്ങനെയുള്ള സംഭവിക്കാം. പക്ഷെ മറ്റുള്ള വേവിലേക്കുള്ള എല്ലാം കൂടെ കടന്നു പോകുമ്പോൾ ഒന്നും സംഭവിക്കുന്നില്ല. അതാണ് ഒരു ലെവൽ ഓഫ് എക്സ്പ്ലനേഷൻ.
Okay, sir. Thank you, sir.
Hello, Professor Vijayan. This is Indulekha from Mahatma Gandhi University.
Oh, hello.
Thank you for a nice lecture. Regarding that cartoon which you showed, vacation and vocation and understanding and appreciation.
Yeah.
It was working. That cartoon was working at two different levels.
Oh, maybe I didn't observe. Let's know. Please tell.
Yeah. If you know, might have noticed that the human child has got the longest childhood. You are dependent on your parents for a very long time, 20-25 years.
Correct. That's right.
Yeah. Now the vacation and vocation are the same for the professor who is a he presented in that cartoon. And the lady is showing so much understanding and appreciation that the processes are nowhere with the family. It is her understanding and her appreciation of the, let us call it, intellectual needs of the person, of the scientist involved, which struck me. When I go to a seashore, even I think of the waves and they're breaking and
but wave mechanics when they go to the sea.
Yeah. Would this kind of understanding and appreciation shown by the lady in this case come up is the question. And the
last line, can you repeat that? Would this kind of understanding and appreciation
show up? If a guy walks along the seashore and absent-mindedly starts thinking about the waves and the ocean currents or the atmospheric phenomena or turbulence and bumps into something, nobody will make any comment. I would like to think while I walk along the road, but if I do that and bump into something, the interpretations will be completely different.
Yes.
So that appreciation and understanding, that's why I said it is many levels.
I use both these words. Both go together, not that it is different from and it's totally exclusive. It's not.
But it is exclusive. That is what I wanted to point out.
Yeah.
Thanks for such a so much clarity.
It's a nice interpretation of the cartoon. Yeah.
Sir, ഇതൊരു സംശയമല്ല. Sir, if you can please describe about topology photonics.
About the
topology photonics. Sir, topology photonics എന്ന് പറഞ്ഞ ഒരു മേഖലയെ പറ്റി എന്തെങ്കിലും സംസാരിക്കാം?
അല്ല, അത് കുറച്ചുകൂടി കോംപ്ലിക്കേറ്റഡ് ആണ്. അത് ആ ലെവലിൽ പ്രസന്റ് എല്ലാവർക്കും ഈസി ആയിട്ട് മനസ്സിലാവുന്ന ഫ്യൂ മിനിറ്റ്സിൽ പ്രസന്റ് ചെയ്യാനായിട്ട് കുറച്ച് പ്രിപ്പയർ ചെയ്തിട്ടുള്ളത് സംസാരിക്കാം.
ഓക്കെ സർ.
സർ, രാമൻ സ്പെക്ട്രോസ്കോപ്പിക്ക് എന്തെങ്കിലും ലിമിറ്റേഷൻസ് ഉണ്ടോ?
ലിമിറ്റേഷൻസ് people ഞാൻ ഈ ക്വസ്റ്റ്യൻ വേറെ തരത്തിൽ ചോദിക്കാം. Why do we need two different spectroscopies to look at the same thing? For example, infrared spectroscopy gives you information about the molecules, molecular vibration in particular. Raman spectroscopy also gives you information about the molecular vibrations. Then why do you need together? Why do you need both techniques? I buy an infrared spectrometer or a Raman spectrometer if I want to do research on molecular vibrations or molecules? The answer to that is there are limitations for both. That is why you need more. Sometimes what you don't see in one of them, you see in the other one, in the other spectroscopy. To be more precise, there are different vibration, modes of vibration. Some of them change the dipole moment during vibration. Some of them change the polarizability during the vibration. So these are the selection rules for observing either of them. So if that is the selection rule itself is the limitation, so to say. So what you can get from Raman effect is depending on that. And one thing which I didn't talk about here, I talked only about molecules. The lattice vibration itself, the whole vibration itself can give you. For example, when I talked about graphene, it is not the particular molecular property rather than the lattice. So the lattice vibration itself can give rise to different Raman modes. So the limitation is that the polarizability should change, then only you can see it in Raman.
Okay, sir.
സാറേ ഞാൻ രാധു. ഞാനൊരു പെട്ടെന്ന് കൂടുതലായിട്ട് റാൻഡം ലേസിംഗിൽ വർക്ക് ചെയ്തിട്ടില്ല. പക്ഷെ പെട്ടെന്ന് നമുക്ക് നോർമൽ ലേസേഴ്സ് യൂസ് ചെയ്യുമ്പം നമുക്ക് ഒരു ഫീഡ്ബാക്ക് മെക്കാനിസം ഉണ്ട്. നമുക്ക് ഇവിടെ ഒരു ഫീഡ്ബാക്ക് ഇല്ല. അപ്പൊ നമ്മള് റാൻഡം ലേസറിൽ നമ്മൾ മറ്റിടത്താണെങ്കിൽ നമുക്ക് എവിടെ ഏത് മിററിൽ നോക്കണം എന്ന് നമുക്ക് കൃത്യമായിട്ട് അറിയാം. വേർ വിൽ ബി ദ ഔട്ട്പുട്ട്. അപ്പൊ ഈ കേസിൽ ഒരു റാൻഡം ലേസറിൽ നമ്മൾ ഔട്ട്പുട്ട് ഏത് ഡയറക്ഷനിൽ നമ്മൾ പ്രിഡിക്ട് ചെയ്യും? എല്ലാ ഡയറക്ഷനും വരുമോ?
അതൊരു ലോക്കൽ ലൂപ്പ് ഫോം ചെയ്യണം. അങ്ങനെയുള്ള ലോക്കൽ ലൂപ്പ് എന്നാണ് ഈ ലേസിംഗ് ഉണ്ടാകുന്നത്. ആംപ്ലിഫിക്കേഷൻ ഓഫ് സ്റ്റിമുലേറ്റഡ് എമിഷൻ ഉണ്ടാകുന്നത്. സോ റാൻഡം ലേസിംഗ് ഒരു പർട്ടിക്കുലർ ഡയറക്ഷൻ ഇല്ല. പക്ഷെ ചില ആൾക്കാർ എന്ത് ചെയ്യുന്ന വെച്ചാൽ റാൻഡം ലേസിംഗ് വേണ്ടി ഒരു ഫൈബറിന്റെ ഉള്ളിൽ വെച്ചിട്ട് ഫോഴ്സ് എ ഡയറക്ഷൻ and you sort of get light only from a unidirection. So that's only way you can make it a unidirection. But റാൻഡം ലേസിംഗിന്റെ മെയിൻ പ്രത്യേകത എന്താണെന്ന് വെച്ചാൽ അത് മെറ്റീരിയലിൽ നടക്കുന്ന പ്രോപ്പർട്ടീസിന് സ്റ്റഡി ചെയ്യാനുള്ള ഒരു ടൂൾ ആയിട്ടാണ്, അല്ലാതെ ഒരു പോയിന്റഡ് ലേസറായിട്ട് ഉപയോഗിക്കാൻ പറ്റില്ല. അത് ശരിയാണ്, ഡയറക്ഷനാലിറ്റി.
അപ്പൊ നമ്മൾ ആക്ച്വലി മീൻസ് ഞാനത് ചെക്ക് ചെയ്യാൻ വേണ്ടിയിട്ടുള്ള ഒരു ഒരു ക്യൂരിയോസിറ്റി ചോദിക്കണം. നമ്മളിപ്പോ ക്യാരറ്റ് ഒക്കെ ചെയ്യുമ്പോൾ നമ്മൾ ഡിറ്റക്ടർ എവിടെ വെക്കും? ഡിറ്റക്ടർ ഏത് ഡയറക്ഷൻ വെച്ചാലും ഓക്കെ ആണോ?
ദിസ് ഈസ് എ വെരി ഗുഡ് ക്വസ്റ്റ്യൻ. ബിക്കോസ് എത്രത്തോളം റാൻഡം ആണ് നമ്മുടെ മെറ്റീരിയൽ, ഇറ്റ്സ് ആക്ച്വലി വെരി റാൻഡം ഓർ ഇറ്റ് ഇസ് നോട്ട് റാൻഡം. അത് ചെക്ക് ചെയ്യാനായിട്ട് നമ്മൾ ഉപയോഗിക്കുന്ന ഒരു കൊഹറന്റ് ബാക്ക് സ്കാറ്ററിംഗ് ആണ് ഉപയോഗിക്കുന്നത് ടെക്നിക്ക്. CBS ടെക്നിക്ക് എന്നൊരു ടെക്നിക്ക് ഉപയോഗിക്കുന്നത്. ഈ ടെക്നിക്കൽ എന്താണെന്ന് വെച്ചാൽ നമ്മൾ സ്കാറ്ററിനെ സപ്പോസ് നമ്മൾ ഇതിന് മൂവ് ചെയ്യണം, ഒരു എന്താണ് ലൈറ്റ് വരാവുന്ന എല്ലാ ഡയറക്ഷനിലും മൂവ് ചെയ്യണം. അങ്ങനെയാണെങ്കിൽ ഈ വീക്ക് ലോക്കലൈസേഷൻ നടന്നു കഴിയുമ്പോൾ അത് വളരെ നാരോ കോൺ ആയിട്ട് കിട്ടും. വെരി നാരോ കോൺ നിയർലി അറ്റ് ദ ബാക്ക് സ്കാറ്ററിംഗ് ആംഗിൾ. സോ ആ കോണിന്റെ ഡെപ്ത് വെച്ചിട്ട്, കോണിന്റെ വിഡ്ത്ത് വെച്ചിട്ടാണ് നമ്മൾ പറയുന്നത് ഇത് മീഡിയം, വെരി ഗുഡ് റാൻഡം മീഡിയം ആണോ അല്ല എന്നുള്ളത്.
Okay, thank you, sir. Thank you.
This is Indulekha again, Professor Vijayan.
Yes.
Would you talk a bit about ring lasers?
Green lasers.
Ring
laser. Yeah. Ring laser, there are a few geometries, and each geometry has its own way of getting the what do you call the in fact dye lasers, the good quality dye lasers are in the ring configuration. It is circulated rather than between two mirrors. It is just not two mirrors. There is a configuration, cavity configuration using different mirrors and all that. See the picture which we have, normal picture which we have, two parallel mirrors and laser happening inside. That's a very elementary picture. That's not the whole picture. The cavity itself can be made, like in the case of random, there are no, you cannot see two mirrors there. It's all distributed. There is another thing called distributed laser where this happens at every stage, not just to end mirrors. So cavity is what people found is if you put the dye in that in a loop form, then lasing is more efficient. And moreover, you can circulate it. If you circulate it, fresh molecule get into the picture and you can continue to sustain the laser action. So this is a standard technique used in dye lasers. One kind of ring laser.
How do you take out the light?
At some point, one of the mirrors, any one of the mirrors. It's like you see, for example, in a particle accelerator also, tangentially somewhere you take out different beams.
Yeah, but
and they're basically going in circles. I don't know, let's see experiment, but something like that.
There is a deflecting magnet in the case of
Yeah. So here one of the mirrors, it's not really, if it is a fiber, you can make exact ring. But then the fiber you can leach out by scrapping a little bit of fiber. And if it's a mirror, you can position one of the mirror which will have which will allow light at some particular intensity, partially silvered mirror, that kind of thing.
Okay.
Equivalent to the magnetic thing, reflection.
Thank you.
സാർ സാർ പറഞ്ഞായിരുന്നല്ലോ, ഒരു വസ്തുവിനെ നമ്മൾ കാണുന്നത് അതിൽ നിന്ന് സ്കാറ്റർ ചെയ്ത് വരുന്ന ലൈറ്റിനെ, ആ ലൈറ്റ് കൊണ്ടാണ് നമ്മൾ അതിനെ കാണുന്നതെന്ന് പറഞ്ഞല്ലോ. അപ്പൊ നമുക്കൊരു ലൈറ്റ് കിട്ടിക്കഴിഞ്ഞാല് സ്കാറ്റർ അങ്ങനെ അല്ലാതെ ലൈറ്റ് നമുക്ക് വരുമല്ലോ. ഇപ്പൊ ലൈറ്റ് പ്രൊഡ്യൂസ് ചെയ്യുന്ന സോഴ്സിൽ നിന്ന് വരുമല്ലോ. അപ്പം ഒരു ലൈറ്റ് റേ നമുക്ക് അത് സ്കാറ്റർ ചെയ്ത് വന്ന ലൈറ്റ് ആണോ അതോ അതേതെങ്കിലും സോഴ്സിൽ നിന്ന് വന്ന ലൈറ്റ് ആണോ എന്ന് എങ്ങനെ തിരിച്ചറിയുക?
അത് അറിയാൻ പറ്റില്ല. ബിക്കോസ് വാട്ട് യു സീ, ലൈറ്റ് വരുന്നു എന്ന് മാത്രമേ കാണാൻ പറ്റുള്ളൂ. ഈ ലൈറ്റ് എവിടുന്നാണ് വരുന്നത് എന്നുള്ളത് കാണാൻ പറ്റില്ല. പക്ഷെ നമ്മൾ സ്കാറ്റർ ചെയ്യുമ്പോൾ എപ്പോഴും നമ്മൾ എന്താണെന്ന് വെച്ചാൽ നമ്മൾ കമ്പയർ ചെയ്യണം. ഫോർ എക്സാമ്പിൾ, നമ്മളൊരു ബുക്കിന്റെ അക്ഷരം എഴുതിയ സ്ഥലത്തേക്കും ബ്ലാക്ക് ആൻഡ് വൈറ്റ് പാർട്ടിലേക്ക് നോക്കുന്ന സമയത്ത് നമ്മൾ അതിന്റെ റിലേറ്റീവ് ആയിട്ടാണല്ലോ നമ്മളത് കാണുന്നത്. ഇപ്പൊ വൈറ്റ് കളറിൽ തന്നെ പ്രിന്റ് ചെയ്ത് നമുക്ക് പേപ്പറിൽ വായിക്കാൻ പറ്റില്ല. അതുകൊണ്ട് ആ ഡിഫറൻസ് സ്കാറ്ററിംഗ് ആണ് നമ്മൾ നോക്കുന്നത്. ഓർ ഡിഫറൻസ് രണ്ട് തരത്തിലാവാം. ഒന്ന് ഒറിജിനൽ ലൈറ്റ് കമ്പയർഡ് ടു ഒറിജിനൽ ലൈറ്റ് ആൻഡ് ദി ഒബ്ജക്ട് ലൈറ്റ് ഫ്രം ദ ഒബ്ജക്ട്, അത് തമ്മിലുള്ള ഡിഫറൻസ്. ഹോളോഗ്രാഫിയിലൊക്കെ ഒറിജിനൽ ലൈറ്റും ഒബ്ജക്റ്റിൽ നിന്ന് വരുന്ന ലൈറ്റും തമ്മിൽ ഇന്റർഫിയറൻസ് ചെയ്യുന്നത്. അപ്പൊ അതേപോലെ നമ്മൾ ഡിറ്റക്ട് ചെയ്യുന്നത് നമ്മൾ ഡിഫറൻസ് ആണ് ഡിറ്റക്ട് ചെയ്യുന്നത്. ഒറിജിനൽ ലൈറ്റിൽ 7 കളേഴ്സ് ഉണ്ട്, വൈറ്റ് ലൈറ്റ് ആണെങ്കിൽ. അതേസമയം നമ്മുടെ ഒബ്ജക്റ്റിൽ നിന്ന് വരുന്നതിൽ ചില കളേഴ്സ് മാത്രമേ ഉള്ളൂ. അങ്ങനെയാണ് ഡിസ്റ്റിങ്ഷ് ചെയ്യുന്നത്. അപ്പൊ പ്രൈമ ഫേസി നമുക്ക് ഒരു സ്കാറ്റേർഡ് ആണോ ഈ ലൈറ്റ് എന്ന് പറയാൻ പറ്റില്ല. പക്ഷെ അത് മോഡുലേറ്റഡ് ആയിട്ടുണ്ടെങ്കിൽ, അല്ലെങ്കിൽ അതിൽ എന്തെങ്കിലും പ്രത്യേകതകൾ കാണുന്നുണ്ടെങ്കിൽ അത് സ്കാറ്റേർഡ് ആണെന്ന് നമുക്ക് ഗസ് ചെയ്യാൻ പറ്റും. ഉണ്ടെങ്കിൽ ഇമെയിലിൽ ഞാൻ കാണിച്ചു തരാം, അങ്ങോട്ട് അയച്ചാൽ മെയിൽ അയച്ചോ. ഇമെയിലിൽ കിട്ടില്ല. C.Vijayan@physics, you can give them the email.
Hi all, I'm here to deliver the thanks for this session. Professor Vijayan has explained the physics of light in the most fundamental level, which is most useful for us students. It is fascinating that such a common question like this has led to such developments in the field of physics. I'm sure that the faculty members would also find it refreshing. So, on behalf of the department and all gathered here, I thank Professor Vijayan for this wonderful talk. Thank you, sir.
It was nice interacting with you. Okay. ശരി, എന്നെ ക്ലോസ് ചെയ്യട്ടെ.